exists. It's not just like a coordinate. It's a whole line. There's not a coordinate. It's a line. A line that doesn't exist. A whole lot of coordinates. Infinitesimal coordinates on a line that don't exist. Okay, so y equals lines vertical or horizontal?
Vertical. No.
If we don't know, we go to try and cut through y equals 2, and we're like 1, 2. Oh, dag nabbit. There's a horizontal line. Also remembering that the x-axis equation is what? And the y-axis equation is? So they could say reflecting on the line x equals 0, reflecting on the line y equals 0, instead of saying x-axis and y-axis. You know, they do that with a little Houdini trickery. Awesome questions. So, if we look here, we have some sort of, it looks like they're getting closer and closer to the x-axis, but not touching. That's what it kind of looks like to me, correct? So where did that happen? What other unit did that happen in? In the unit in the textbook. In exponentials. In exponentials, we had a horizontal asymptote on the x-axis, correct? And what moved it? Vertical translation could be the only thing that could move it, right? That would make our asymptote change. So if we had a horizontal asymptote of y equals 0, we moved 7 up, it's now at y equals 7, right? So our asymptote in exponential is based that way. Well, we have one here, it looks like, wow, it is on the x-axis, right? So I would guess that my horizontal asymptote would be, I'm going to need a pen, it's going to get mad at me, would be y equals 0. I appreciate the fact that you said y equals 0 and not just 0. 0 is just a number. I don't even know where that is. There's so many zeros, so little time. You know what I mean? So we're going to do that. Then I had an educated guess on the x one. Where did we guess where the x was happening? Well, it's not at 0. It's a little over. It's not at 1. It's a little over. You're guessing? Half? Where could we get that from? From the denominator. Your vertical asymptotes are just your non-permissible values, right? Whenever you guys learned rationals last year, you had a whole unit on it. It was wonderful. It was the best of times. It was the worst of times. There's so much factoring, makes my heart sing, but not most students. So you learned about non-permissible values. You learned, hey, where the denominator can equal 0 is a problem, right? You actually, your NPVs, every single time you solved last year, you were finding asymptotes, vertical asymptotes, okay? Domain and range are extremely easy in rationals, if you can find the asymptotes, because it's everything but that. So, my domain here would be, I don't want my board to shift, x such that x can't equal 1/2, but it equals everything else. That's what such that x and the reals. Only one that doesn't exist? Yep.
How would you do that extent?
That's
in the interval.
Integral. So you're going to go negative infinity to 1/2, round bracket, or 1/2 to infinity. The only thing you're not including here is square brackets, so 1/2 is the only thing that's not included. And then same thing with range. What's the only thing that doesn't exist? 0. So we would say y such that y can't equal 0. Y is an element of the reals. That's an infant. It's getting worse. Okay, negatives. Okay. Cool. I want you to now type in, ready? It's not on here. You're typing in your own version. Ready? It is y equals -1, 3x plus 1. I want the vertical asymptote, horizontal asymptote, domain and range. You can think it. You can write it on a separate sheet of paper. I don't really care. But we're just practicing. Like I said, you can do it on a separate sheet of paper, whatever you want, but we're going to practice one example after each example on the chart. So, typing it in. Did you type it in? Or does it look like my horizontal asymptote's at? The x-axis, which is y equals 0. So I would say horizontal asymptote. And when my vertical asymptote? And you got there. You did. So we just take this 3x plus 1 and we say it can't equal 0 if we're doing our MPDs. We subtract 1. We get 3x can't equal negative 1. We divide by 3 and we get x can't equal negative a third, which is actually the domain, correct? The asymptote exists there. So you put an equal to sign when you say asymptote. The asymptote is here. It's equal to this. Because the asymptote is where the graph doesn't exist, right? And then my domain in set would be x such that x can't equal negative a third, but x to down with the reals, so it's everything else. And my range is y such that y can't equal 0. We'll do interval in the next one. What's the degree of the domain? Degree of the numerator, degree of the numerator is 0. There's nothing there, right? So I could write x to the 0, could I not? So the degree is 0, it's a constant. What's the degree of the denominator? So is my numerator a smaller degree than my denominator or a larger? Smaller. Let's go back to our little notes, This is a rule, and this rule will make sense when we start using limits. Now you're just trusting me, okay? So if n is less than d, if your numerator is a smaller degree than your denominator, and this is totally based on the degree, your horizontal asymptote, and these are the horizontal asymptote rules, because the vertical asymptotes are easy. They're just the non-permissible values, right? If the numerator is a lesser degree than the denominator, you will always get y equals 0. Always, always, always. If you don't believe me, let's look at C. And by C, I mean the third one. Why did I say it's C? This one. Put that one in. This one right here. And this works when you have full numerator over full denominator. So these rules only work if you have a whole numerator over a whole denominator. So do you see I bypassed the second one? The second one doesn't have a full numerator over a full denominator, does it? No, we're bypassing that one. Guys, how are we going to get non-permissible values for this one? We're going to have to factor it. Factor. Decomp. Go, go, go. Boy, they're going to really like to hear you guys talking.
Oh, and so you've been recorded this whole time.
Yeah.
That is cool.
Okay. So this is grade 11 at its finest, except it wasn't not equal to 0 at the time, it was equal to 0, right? Just solve them. It's the same thing. It's just now that our denominator can't equal 0. So we have x can't equal negative a half, and x can't equal 3. Well, that's my domain, right? But my asymptotes, are they not equal to? Or are they equal to? They're equal to. It's where the asymptotes exist. Now, x equals 1s. Let's look at this graph. So we're going to have so do we have the asymptotes where we said they are? The asymptotes we said were going to be at negative a half and 3. Let's check it out. Negative a half, that seems reasonable. And then 3. I think my window is set weird. I had it set to a trig window, that's why. And then negative 2. So 3. So those look real. And then where is my horizontal asymptote at? 0 again. What? The numerator's degree what? The denominator's degree what? Is the numerator a lesser degree than the denominator? Yes. So I know that, we'll go back. I know that immediately if this is a lesser degree than the denominator, it's going to be y. Oh, I love you, Lord. You're my favorite. Trying to like go with positive reinforcement with it to see if it works out. And then this one's going to be x equals negative a half and x equals 3. Using limits as you approach infinity is what's going to, positive infinity and negative infinity is what's going to actually show us why this rule works if your numerator is less than your denominator. But right now, we're not there. We will be there even before your diploma, so you could even use limits to explain it. They'll be like, what is this child doing? They're so smart. You'd be like, thank you. I know. Thank you. All right. So if we do set notation just for practice, this one is going to, oh goodness, this one is going to be negative infinity to negative a half, not included, or negative a half to 3, but still not including them, or 3 to infinity. Set notation, it would just be x can't equal negative a half comma 3. I'll show it. X number. And then this one would just be, why did I, negative, that's an infinity sign. I didn't want to erase. And then are the last two smaller, yep.
What are the V's and the U's in between, Steve?
The U, they're all U's, they're not V's. The U's mean or. Yeah, it's a union symbol. So in mathematics, this is a union symbol, and it means or. And the reason why you use it is you can have a piece of your graph that's here or it's here. There's no such thing that exists here and here, because it's like you're either this way or you're this way, but you can't be in both spots, right? Yeah. This means intersection, which you're not going to use. And it's and they use this in 30-2 all the time, actually, because they do set theory. If you do stats in university, it uses a lot of 30-2 and 20-, but not a lot of your math. I don't know. So, look at the last two. Is the numerator smaller than the denominator? Nope. Okay. What about this one? People will say the second one. They'll say the numerator is smaller than the denominator. But what did I tell you the rule was?
Degrees.
Yeah, the degrees and
Whole numerator.
whole numerator over whole denominator to use horizontal asymptote rules. Okay. This one we're actually looking at tomorrow. This is the transformed form. This is going to be a vertical translation. This is going to be a horizontal translation. That's a vertical stretch. We're dealing with this tomorrow, and then we're going to fill this part in tomorrow. Okay? So we're going to these two. So type this one in. See if you can give me the horizontal and the vertical asymptote. You're a hand in? Yeah. You're being recorded. Does the rules of the numerator degree and denominator degree at all affect the vertical asymptotes, which are your x-asymptotes? What are they only based off of? Your non-permissible value. Okay? But what about my horizontal one? Where does it look like it might be falling? My horizontal? It actually is. So it looks like it's falling between -1 and -2 on the y, right? Like it looks like it's possibly somewhere in there. We agree? All right. It's actually -3/2 because there's a rule. Look up here. The degree of this one is degree what? The degree of this one is degree what? So when the numerator and denominator equal, have the same degree, your y equals your a over c. Your y equals the fraction of your leading coefficients. Leading coefficients is the important part. So the number in front of the largest variable exponent. That's where we're getting y equals -3/2. And then this one we said we'd go -2x plus 3 can't equal 0. -2x can't equal -3. X can't equal 3/2. That would be my non-permissible value, but my actual asymptote would be x equals 3/2. Right? So they're actually very similar spots. So the domain of this one is going to be x such that x can't equal 3/2. And my range is going to be, I don't know why I put the R there, y can't equal -3/2. You try this one. Go. So, this one here, we do the leading coefficient. People will tell me it's a half. Watch yourself. You have to take the leading coefficients. So it's y equals -5/4. Don't fall to the front numbers. Leading coefficients. Leading coefficients. Do you see how they can put it out of order and then they'll just put a half as an option? Not a half, -5/4. And then your x equals -3/4. And then x such that x can't equal -3/4. X and on the reals. Y such that y can't equal -5/4. Computer is lagging, not letting me write. Okay, so we dealt with the rules of if the numerator is small and the denominator is always y equals 0. If the numerator is equal to the denominator, it's a fraction of leading coefficients. We agree? What happens if the numerator is greater than the denominator? If the numerator is greater than the denominator, you don't have any horizontal asymptotes because you have slant asymptotes possibly, which we do not have in 30-1. They only come up in calculus, so that's not an option. So the only other option you have, if your numerator is greater than your denominator, is a point of discontinuity. And let's see why. So here, point of discontinuity is a coordinate on the graph of a function that is not continuous. It's a hole in the graph. So the graph looks like it's continuous. Your calculator, no matter how hard some of them, you zoom in, you're not going to see a gap. The only place you're going to see the gap is actually if you look in the table of values, or you go second trace, x is this, and then they'll tell you there's no y, because there's actually an open spot. Okay? It occurs when the numerator and denominator of a rational function are simplified by dividing out the common factor. This missing single point is represented by an open circle in the graph, considered to be a hole. We call it a point of discontinuity in 30-1, and in calculus they call it a removable discontinuity, which means they just take it out. And when we do, so we're going to call it point of discontinuity, because that's what they call it. So here we have a function. The function is larger. It's a degree 2, the denominator is a degree 1. We factor the numerator. These bad boys cancel off, and the moment they cancel off, it's a point of discontinuity. Okay? So the moment your actual coordinate or factor cancels, you have a point of discontinuity. Okay? So yes, x can equal 3. We know that. We agree with that. That is an NPV, correct? But if the factor cancels off the top, it is not a vertical asymptote. It's actually a point of discontinuity. Okay? And when you look at it in your graph, you're going to see. Because look at this. When this cancels off, this is what I'm left with, correct? So if you look here, it's just drawing a line. So on your calculator, you're going to type in this rational, and you'll be expecting like the woo and the woo, and then you'll look at it and you'll be like, this is a line. What the heck? Be suspicious. It's a rational still. So there must be an open point somewhere. Okay? Now determining the x value of the point of discontinuity is just a normal, acceptable standard question. The moment they make you find the y coordinate of the point of discontinuity, it is a standard of excellence question. And so when we get those on the diploma, I'm just like, thank you. That is an easy standard of excellence. I will take that. I will take that as one of your standard of excellence questions. Okay? So the x value is really easy. The x value is just x equals 3, right? Oh, why did it move? I have to stay away from the board. I'm a board cuddler, I've decided. Because if you're anywhere near here, it literally functions. I need to not be a board cuddler. I need to be like out here. I didn't know it was a thing until this board happened. So x equals 3 is the x value. How might I get the y?
Plug in 3 for x.
Yeah, plug in 3 for x into the what? Into the simplified version. If I plug it into the original, I'm going to get zeros, right? Because I'll have 0 on the bottom, 0 on the top, it would not be helpful. You are going to plug it into the actual graph that's left over. So I plug it into the function that's left over. I plug in the 3. I go f of 3 equals 3 minus 2. F of 3 is 1. So I know I have a point of discontinuity at 3, 1. So all I do is I draw the graph of x minus 2, what's left over, and then I go to 3, 1, and I draw an open dot. Like that. That's it. Now, your domain and range are going to actually represent that as well. Your domain is going to be not equal to 3, and your range is going to be not equal to 1, right? The point of discontinuity needs to be also involved. So whenever I give a test question on this, people will give me the domain and range correctly, and often forget either the x or the y of the point of discontinuity. Because we can have a rational graph that looks like the curvy thing, and a point of discontinuity in it. So it might use both rules. Let's look. So, flip over. Let's look at this first one. Actually, we're going to look at C first. So if we look at C, we have 2x squared plus 5x minus 3. Looks kind of similar to what we did. So we go 2x squared plus 5x minus 3. We get 2x squared plus 6x minus 1x minus 3. Take out a 2x and left with x plus 3. Take out a negative 1 and left with x plus 3. And I'm left with 2x minus 1, x plus 3. Wowzers! What's happening here, people? Oh my gosh, the x plus 3s are canceling. What would that mean? What is my point of discontinuity at? What's my x? Negative 3. How for art thou will I get my y? Plug it into the simplified. So I'm going to get f of negative 3 equals 2 times negative 3 minus 1, which is negative 7. So this function is what is actually being drawn. The y equals 2x minus 1 is what you're going to actually see. You're going to draw a line at 2x minus 1. But then you're going to go to 3 and negative 7, which is on the line, and you're going to put an open dot. If your open dot is not on the line, you either drew the line wrong or your dot is wrong, because it needs to be on the actual graph. So when your numerator is larger than your denominator, you get a point of discontinuity. That's it. What happens if they're the same? If they're both degree 2, that's where you could get a slant asymptote, but we can't. So when they're degree 2, both degree 2, you will get an asymptote, vertical, horizontal, and a point of discontinuity. You're going to get both. Because when we canceled this off, we were left with a line. When we cancel these ones off, we're going to be left with a rational, right? Which gets us a horizontal and vertical asymptote and a point of discontinuity. So let's go to a separate page and do this one. X squared plus 5x. All over x squared plus 7x plus 10. So we factor the top, and we're left with x plus 5. It gives you room below to put, like, show your work below. You guys have below work in the A and the B and the C. Over x plus 2, x plus 5. These are going away. What am I left with? A line now? Am I left with a line? No, I'm left with what I had in the previous questions, correct? I'm left with a rational, am I not? I'm going to ignore the point of discontinuity for now. I'm going to say, hey, there is a point of discontinuity, just to remind myself. What's my x going to be of it? Negative 5, right? I'll find the y in a second. Go back to my rules. If I have an x plus 2 in the bottom, what does that get me? Vertical asymptote, right? Your x equals gets you vertical. So I'm going to get a vertical asymptote. At x equals negative 2. How do I get my horizontal asymptote? Leading coefficients, because degree 1, right? So my horizontal asymptote is going to be what? My domain and range? Well, I first have to find the y of this one. How do I get the y of the point of discontinuity? What was it? Plug it into the simplified. So I'm going to go y equals negative 5 over negative 5 plus 2. So it's because I'm plugging it into the simplified one. So I get negative 5 over negative 3, which is 5/3. So do you see how people will put this in their domain and range and forget these? You're going to have two numbers in your domain, you're going to have two numbers in your range, right? Because these don't exist as well. So your domain is going to be x such that x can't equal negative 5 and negative 2. It's in your chart. I'm just being lazy and not going back. And then the range is going to be y such that y can't equal 1 and 5/3.